So over the last 7 years, I had lots of fun working on decadal predictability and decadal predictions with my NCAR colleagues, but I also had headaches. So today, I kind of want to go through those headaches to motivate discussions. I will go through a list of questions first, and then I will explain each question with an example. The first question is predictability and prediction skills. Are we getting consistent answers? Second question relates to bias adjustment. Are the better handcuff results caused by initialization or by bias adjustment? Third one, initial shock. Are there returns of skill after the initial shock in CCSM4? Alicia and Steve already introduced our prediction system at NCAR. We use two kinds of initialization methods. One is the DART assimilated ocean, and the second one is the forced ocean. We call it the core. So because we have a complete set of the core initialized decadal predictions, so my analysis here are primarily focused on this course or the handcuff set of decadal predictions. The fourth question concerns the non-stationary errors. And the last one, the forecast verification. So the first one, I am definitely not as sophisticated as George and Arun. I ask simple questions. When I look at analyze our predictions, I ask myself, are we getting consistent answers? Here on the left-hand side, I show George's famous plot showing where there are strong initial value predictability and a forced predictability. So the initial value predictability are higher at the mid-latitude and higher latitude ocean, and the forced predictability is stronger in the tropics. On the right-hand side, I show the prediction skill in CCSM4 SST year 3 to 7 predictions. So the top panel is just anomaly correlation coefficient, and the bottom panel shows the detrended, the correlation from the detrended anomalies. So by comparing these two panels, it's very clear that the stippling shows the AR1 significance level. So by removing the trend, we're losing lots of skills in the tropics, and so we only have skills left in the Atlantic and the subtropical Western Pacific, and some scattered regions in the Southern Ocean. So I think my first reaction was, okay, this is what we expected from our predictability study, but I still have struggles. For example, like 2 years ago, Champing asked me this simple question. Hey, if you initialize the ocean, how long do you think it will affect your prediction? Well, it's complicated, like mentioned by George and Arun. If our model has some systematic, have some climatologic bias. If we kick the model hard enough, and the models are the initialization kick the model off its regular trajectory, it's a very complicated answer. So I do not have a quick answer, as the predictability study says. Plus, predictability estimated from a perfect models is like a very general, like average estimate. There could be more predictable patterns and more predictable initial conditions. And my biggest pain over the years is the IPO or the PDO. And like after these years, I still struggle with it. Is the IPO or PDO predictable? And so I asked my supervisor, Jerry, the same question. And he said, I don't know. And so I think maybe I am just too naive to ask this question. Maybe everyone in the audience, they already know, they're even reluctant to ask this question. If the IPO or PDO is not predictable, what's the point of like trying to predict it? And my second question is caused by the bias adjustment. Here I list a few bias methods we commonly talk about in this field. The first two methods are recommended by the Clever report. The first one, we calculate the time evolving drift. At each lead time t, we calculate the drift from observations. The second method is recommended for anomaly initialization. We simply remove the climatological bias over a climatological period. The third method, I call it the Nominee Method. This is the method Steve Eager talked about this morning. We simply calculate, the model drift is implicit in this calculation. We simply calculate the departure from each prediction from the average prediction. And this method has been used by lots of groups, but it was not included in the Clever report. Keyring method. Well, I had some struggles with this method, frankly, partly because it's, it's a heavy massage on the prediction, and also it was kind of hard to apply it to multi-models on each, not just for globally average temperature. If we want to bias correct at each grid point, you have to worry about the conservation of the energy, temperature, and so I find it kind of hard to apply to multi-model analysis. And of course, there are lots of other bias adjustment methods. If we ask Arun, he probably will come up with like 10, 20 bias adjustment methods. And most of these bias adjustment methods, they aim to make the predictions look nice, and except the anomaly method. And so I'm going to use this anomaly method for my analysis. I don't know what's happening here, but it doesn't matter. So 2 years ago, Jerry and I did a simple analysis, multi-model analysis, looking at the semi-flight predictions. We looked at 2 case studies, trying to look at the start years from the year 76 and 2005. And indeed, well, for this analysis, we used the bias adjustment method recommended for the full field initialization. And we see after we made the bias adjustment, which is represented by the red line here, and we compared with the results from the uninitialized runs and bias adjusted uninitialized runs. And we saw some improvements, but these are just 2 case studies. And we are not sure whether this improvement is caused by bias adjustment, or, for example, if we constrain the initial condition, we're supposed to get better results. But this does not mean we can predict the evolution better given the initial information. So this is one struggle I had. And the third headache caused by the initial shock in CCSM4. So this is expected because we all know our models are not perfect. And this plot I'm showing, comparing, the color does not show up here very well, but I'm comparing the equatorial wind stress in the core data, which is the red shading, and the uninitialized runs, which is represented by these blue lines. So it's clearly our model underestimates the trade wind at the 3-4 region. And consistently, this is the model free runs, uninitialized runs, upwelling at the 3-4 region. And the red line shows the month 1 prediction of the upwelling. So our model has weaker upwelling in the equatorial, in the 3-4 region. So once we push our model with these initial conditions, it will drift back to the blue distributions. And this takes about 3 to 4 years. But we didn't expect our drifts are ugly. Here, I'm showing the 3-4 SST, the raw prediction from each starting years from 1955 to 2010, from month 1 to the end of the year 10. So each color here represents a particular start year. The early start years are represented by the blue color, and the later start years, the red color. The black line is observations. So for lots of early start years, we have this warm drift, 2-degree warm. And some years in the 90s, the model gets like 2-degree cold. So this is the problem that have been noticed by some other modeling group too. And this drift behavior can be caused by a coupling error. In this plot, I'm plotting out the thermocline depths from each start year. This is the month 1. Oh, this top panel. Okay, this top panel is the core data, and the bottom panel is the month 1 prediction. So by just coupling for a month, you can see probably does not show very well here. This is the 3-4 region, and by just coupling for a month, these red lines and blue lines are more separated than in the core in the initial condition. So this is an indication that the initial errors are amplified by the coupling. I actually did some budget analysis. It's not just the temperature, it's the temperature, the currents, they all contribute to this different drip behavior, and it is very difficult to pinpoint which is the to single out one single term. Now I'm going to show you a few snapshots. This is month 1 here. If we just look at the month 1, each prediction is represented by a red dot here, and the black line shows the observations. So our initial condition is okay, but by the time of the month 10, you can see due to this odd drift behavior, these early years, they're very warm, and later years, cold. And after 5 years, the amplitude drops. And it's very hard to say from this plot whether there are returns of scale. Now I'm going to check, and I ask this question frequently: are there really is there a return of scales after the initial shock? So again, this shading, I had some nice shading in this. They do not show up here, but the red line shows the anomaly correlation with observations each month from month 1 to the end of the year 10. And the red line is the average, the ensemble mean anomalies. And I have some shadings to show, because we have 60 star years, we have 10 to 60 combinations of predictions. I only sampled 1,000 combinations to look at the possible correlations. And the shading shows, if you look at this beginning part, we're very happy that the scales are as good as the current seasonal prediction models. But I think what we are more concerned here is whether there are return of scales. And if I look at all the combinations and look at the possibilities, the possibility is very low. And this is to follow up Yushi's talk. Of course, I'm always interested in whether there are more predictable patterns, and so I followed his work, and unfortunately, I do not see good scales associated with the intrabasin variability pattern in our model. I'm not complaining, I'm just saying, right now, our model still has problems, and we are not having this, we tried other patterns, and we're not finding good predictability or scales. And another question, non-stationary error. So I remember earlier today, Gokhan said, our core data is very good. And I'm going to challenge him. So this plot shows the thermocline depths at this eastern end of the 3-4 regions. The red line is the estimate from the Levitas from year 1955 to 2014. The blue line, our core.
You shouldn't use Levitas for this, so I trust core better than Levitas.
This is going to be my question. What should I trust?
Levitas is heavily smoothened there, and then there's a lot of essentially issues with Levitas. You can use the consolidators.
Anyway, I think this is one. Anyway, this black line, the core data, has a very obvious trend. Is this real? I mean, blame the Levitas, but is this real? And it is causing our our model problems. And so GoCon, you have to figure this out. And Jerry and I also look at the precept. Of course, we all want to find some skills in precept. And we look at the UFs using the anomaly adjustment. We look at the UFs of the year 3 to 7 average prediction. And this is the time series of the summertime and wintertime PC1. And this UF1 looks just like the observation regressed pattern. It looks very nice. It shows a shift. The shift we hope to get, and it's very nice. But if we keep the picture in mind, how the model drift, we have to worry whether this is the signal we hope to get, or this is just something caused by the drift. So it's an unsettled issue. It bothers Jerry, it bothers me, and we're still working on it. And the last question, forecast verification. When I was buried in the prediction and in the analysis, I tend to chase the good results, and then sometimes I get lost. I forgot what we're trying to predict. Are we trying to predict a good case, find some good cherries, or are we trying to predict a cycle of oscillation? So, and after I get some good cherries, I kind of feel, are these things predictable? And I think this is a plot. This is a plot showing, Jerry and I had a paper on this. We showed there are some occasions you can find really nice patterns. And there looks like there are some promising aspects of decadal prediction and IPO, but I'm losing the, okay. But we also have problems. What are we trying to predict? I think Jerry will explain that plot at his talk, so I'm going to save time and skip it. And so at the end, I'm going to summarize my questions with only one question. What shall I do? What shall we do about this? And one thing Jerry asked me this question too before I came here. And so I kind of like Arun's suggestion. I kind of feel something is kind of missing in the component C, which is predictability. We're trying to set the pacemaker runs, trying to, I think, but I mean, it is like we set the pace of the Pacific, we set the pace of the Atlantic, and we'll probably get good results. But I feel the key is whether these things are predictable. For me, I believe there are long predictability in the Atlantic, but the stumbling block is the Pacific. Is the IPO, is the PDO really predictable? What are we going to do about it? And I kind of feel like right now, at least for CCSM4, we have this model drift issues. We're still working on it. I'm not giving up. But I just feel at this stage, maybe we could also do some perfect model predictability study and see, suppose if we get this Atlantic pattern, can this pattern cause or produce some signals? And suppose we want to predict the mid-70s shift or the hiatus. If we get this initial condition, how long can we get skills? So I feel like there's still some space or some work needs to be done within the perfect model predictability framework. And my second comment, I really like Alicia's effort comparing the model ocean initial condition. And I think this is something this group can do, because if we want to tell the public, these are the ocean informations that will bring us the skills, we probably should first look at our models. If in our models, all these ocean initial conditions, we're not sure about it. They're all scattered around. How are we going to convince the public these are the information that bring us the skill? So I feel maybe we could, like what Alicia has already been doing, we could compare the ocean initial conditions, and at least, like, Gokang, you can tell me what ocean initial conditions is the one that we should trust the most. And I feel this is the different area that the seasonal forecast people probably don't worry about the 60s and the 70s, but this is our challenge, and we have to face it. That's it.
Okay, thank you very much. Any questions?
No more questions, because I already asked all the questions.
Any answers then?
You need to provide the answers now.
Yeah, Arun.
I think your point number 4 is one of the biggest headaches in the seasonal prediction is. So you get these non-stationary biases because of the non-stationary of the initial conditions, which are spurious. And each time you have made the model upgrades, these things slip through and make it's almost impossible to bias correct the forecast because there's this non-stationary in the initial conditions, which are spurious versus getting the forecast. One period would have a different bias, other period would have a different bias.
Gokang?
It's not a question trying to provide a comment for it. I mean, for example, regarding ocean initial conditions, when I, for example, gave these core 2 comparison talks, and there are all kinds of AMOC, for example, states, and then the comment that I generally get from the people is that, well, why are you bothering to use or doing these hindcast simulations? Because core simulations are also used, as you said, initialization of decadal predictions. Now, why bother with core if all these models showing all these different results in the mean states? You can just simply use reanalysis products. So that sort of, those comments was the sort of were the basis of the study that Alicia is essentially leading. And the thing is that there was in general, and I mean, there may be still in the community, that there's the misconception, in my view, that the reanalysis products are much better than hindcast, and they produce the, I don't want to be too strong, real state of the ocean. But as you can see, they are, in my view, all over the, I'm biased towards forward models, of course. They are varying quite a lot. And then people, each group is happy with their initial condition, and they're not necessarily going to give up their initial conditions. So I'm not sure what to say in terms of ocean initial conditions.
Well, but that's not Teng. She's
I know.
just pointing out that there is this non-stationary
Yeah.
hindcast.
No, I was just changing
Maybe.
the initial condition.
Okay.
2 comments about the list of questions. I think that seasonal forecasting is concerned by all of them in same measure or even more than decadal prediction. So that's something that I think it's important that we don't lose sight that there is another community that is not here, that is affected and is investing efforts in exactly the same kind of problems. The other thing is something that you mentioned about biased adjustments, and I think you expressed it as if, I don't remember exactly the words, but it was something like we use bias adjustment to make things look pretty. I don't know if that was what you intended. What I think we are forgetting here is that there's a group of people out there that are not here that are called users. We don't care about bias adjustment. So actually, I prefer looking at the model output itself without any bias adjustment because the model lives in the model world. The problem is that the users don't know what the model output is. That's what we need the bias adjustment for, not for ourselves.
When I said that, I said all these methods except the anomaly method, they kind of massage the output. And that's why I prefer using the nominee method.
Massages the input.
John?
Under the initial shock part of your talk, the example you gave was the fact that CCSM has bias in the trades in the upwelling.
That
Is that a systematic bias across models? If it was, then it might be helpful to know that in terms of the issues that Matt Collins raised in terms of models, not producing a cooling trend since '79. None of them really. Models just don't get a cooling trend.
I think that most models have this code bias. That's and I'm not sure. I think here this is. I don't know. I cannot make any comments.
It ties to the trades.
Yeah.
Joe?
And so in the category of this initial condition kind of problem that you identified, it kind of ties into what Alicia was talking about, is that when you look at across the modeling groups and what methods they use, and we had a table we were looking at from chapter 11, most of them use some kind of ocean reanalysis or some kind of simulated data. But the thing we've never intercompared or collected to intercompare are what those initial states look like across the different initialization methods. So you can imagine, say, if we decide that November is going to be the initial month, or even just the first year, an annual mean, you could plot time series of your initial states for all those initial years and compare that to observations, whatever observations you have. And that could give you an idea of what the initial states look like. Because I would assume what would happen would be the core force would have bigger errors compared to observations and say DART, because DART's bringing the model back to observations, but then you've got to have bigger bias adjustments because the drift is bigger. So I don't think we've ever really tried to assess that aspect of
I feel.
time prediction, which is what you're highlighting.
I feel one missing part is because Alicia and her collaborators put lots of efforts in the Atlantic, and if we are at least this is what component C is going to emphasize, both the Pacific and the Atlantic, and we need to come up with some suggestion. What are the key ocean observations, ocean initial conditions we should care about? And I think this is also good for the future monitoring. We want to monitor the oceans, and then we need to find out where are those hot spots.
I mean, just to add that, we can ask essentially the decadal component A or whatever, people can provide ocean initial conditions.
Right.
I mean, people, for example, claim that they are getting really high prediction skill because of their ocean initialization, but if their ocean initialization looks like garbage, then we'll know that there's something else is going on. Maybe garbage works.
Yeah, but see, it's a combination of that with the size of the bias adjustments, the effect of the bias adjustments, and actually, as Haiyan showed, you can actually get correct an erroneous trend in your model by the bias adjustments, just because that's where you compute the bias adjustments. So it's a combination of the initial state errors and how big the bias adjustments are. So it's that combination. So just by having initial states that don't exactly match observations doesn't tell you how skillful you're going to be, because maybe your bias adjustments are bigger, and that's going to give you better.
Well, it's almost coming back to whether you should have the best ocean state to initialize it, or another state that's going to be useful for the decadal predictions.
Yeah.
But, I mean, just the component A proposes to collect a certain set of monthly mean data.
Yeah.
I mean, those data will be available.
Not the initial conditions.
Well, what do you mean by initial conditions?
Tell me what the
This is
ocean
your
state
first-
is in
well, This is
November.
your first month's forecast. Isn't that close enough?
Maybe.
Maybe, but I showed in the summer client depths, it's just 1 month coupling. You can see there are noticeable changes. Like here, this just by couple for a month, the red lines or cluster here and the blue here, and it's not that clear in the core initial condition.
You're doing a 1 month. It's a 1 month average you're looking at,
She's saying it doesn't necessarily reflect the initial.
It does not necessarily reflect the errors in the initial condition.
What does it reflect then?
It's a coupling error. It's already showed up in just the first months.
So that's why you want to do the transpose CMIP.
Yeah.
Error is big in 5 days.
Okay, 2 last questions, Rim, and
No, you should change that in your translation.
Comment, I think the last CMIP 5 exercise, Decadal prediction exercise, taught us a lot about this initial condition, and I found it really useful to have this core forced initial condition with respect to the data assimilation, and I don't agree with Broken that the centers just want to stick to the initial condition and they don't want to do anything else. The reality is we are struggling to provide good initial condition, and even if you look at the assimilation, like Alicia showed, like the AMOC is all over the place, and we don't really understand how to produce a good AMOC initial condition with data assimilation. And the truth is, it's easier to do it with core because you only put the atmospheric forcing, and you know that the atmospheric forcing, like the MEO, is going to produce this increase of the AMOC. But as soon as you put data there, you constrain your system and you degrade it. And so we choose to go toward that path in many centers by using initial conditions that include data, and then we realize that we have worse initial condition. And this is a fact, and we are making progress, I guess, in all the centers that produce this initial condition, and we are really kind of learning along the way. And another thing is, I believe we could have wrong initial condition or bad initial condition for the AMOC, for example, but maybe skillful prediction, because you initialize other things like temperature, salinity that gives you the velocity, and your initialization, then you let your model free, and it can produce a variability that is proper to the model, even if you initialize it in a way that you know shouldn't be, it's not what like you would expect. So I think it teaches you that too. So I'm not sure even if you provided the users all the state estimate, they could tell you a priori which one would give you a good forecast for the good reasons.
I'm not suggesting there will be one answer for observations, but I feel at least for this, like when Jerry and I look at the precepts, I feel we should keep in mind there are problems in our initial condition. And when we interpret the result, we should always wonder whether this is signal or this is the problem caused by our initial condition.
right, last question from Noel.
It's more a comment about this discussion about the initial condition. I think it's a good idea to correct initial conditions, but actually, if you're looking at things in the ocean, we don't know the observed state. When we do data assimilation, it's to estimate the observed state. So it's probably, when you want to compare your forecast system, maybe you should compare against the forecast, the initial condition that you use, the initial data that you use, because that's what you take as truth. I think the interesting thing is to compare, once you've done the forecasts, you can compare against something that is maybe a better observed quantity, maybe SSD, and you could get an idea whether the initial ocean state was more realistic than that data assimilation or force drives or so.
Yeah, plenty of issues. Maybe we can return to them on Thursday, perhaps. So just thank the speakers one final time.